Gold nanoparticles power bio-nanotechnology, drug delivery, biosensors, diagnostics. Whether they work comes down to two numbers that are slow and hard to measure: their size distribution and whether they're clustered. We built the tool a nanoparticle lab was missing to measure both, automatically, from a microscope image. We built it for the Dragnia lab at Indiana University, which packages gold nanoparticles inside virus-like particles for theragnostics. The biology is gated by particle size and how the cores cluster, and that clustering rewrites the optical spectrum. Today, they read it by hand-counting hundreds of particles, with no way to quantify aggregation from the spectrum. Hand-counting is the bottleneck. Slow, only a few hundred particles, and biased by which outliers get picked. And two batches identical by size can behave completely differently, because one is aggregating, and a dried grid can't see it. So, we built the whole pipeline. A microscope image goes in. Stage 1 segments every particle, classical or a segment anything foundation model for aggregates, with one-click human review, producing a per-particle size table. Stage 2 feeds that into a physics model, me theory through exact multipole electrodynamics, and it's trustworthy. Where the classical method merges touching particles into blobs, the foundation model separates them. Claude code wired it in and validated it against the lab's hand measurements, recovering the true size where thresholding fails. And not just one field. Across all 8 samples, the automated size distributions sit right on top of the hand-measured ones, within 6% from up to 6 times as many particles. Then, the payoff: we predict the spectrum from size alone, with 0 fitted parameters. For every clean sample, the peak lands within a few nanometers. But the 2 boxed samples break, far redder than single-particle physics allows. That gap is the aggregation signal. To turn that into a number, we first got the monomer line width right. And line width is chemistry. Calibrated per synthesis route, our particles sit on the opposite side of textbook gold, so the plasmon width doubles as a crystallinity probe. Watch the pure 12 nanometer control, top left. Before calibration, it read a false 13% aggregated, after 0. The real aggregates don't collapse. Their red-sided misfit is genuine coupling, not line width. Then, exact electrodynamics puts numbers on the rest. The flagged batch carries about 1/3 of its gold in clusters, the larger sizes roughly 1/2 to 4/5. Only the total fraction is identifiable, which is why size comes from the TEM pipeline. So, the lab now has one pipeline that turns a microscope image into size, distribution, and cluster state. In minutes, not an afternoon. 2 open-source repos, MIT licensed, built this week with Claude code, the segmenter they run, and the physics that reads aggregation off the optics.